And greetings, everyone. Welcome, everybody. Welcome to the Evidence and Reasons for the Christian Faith uh, Academy, Evidence and Reasons Academy. This is a sister channel to the Evidence and Reasons for the Christian Faith video channel. The reason that I separate out the channels is to have things like nerd torture sessions where we go into things in a lot of technical detail. It's not of interest to the general audience. So this channel is like 14 times smaller than the main channel. But this is where we can put as a matter of record the very difficult technical discussions that are relevant, especially to the creation evolution controversy. We may have some history shows or whatever, but this is going to be just really, really heavy on science. I'm privileged to have Jordan K here, and he's going to talk about his analysis of a Creation Research Society paper by Rotta. I actually was hoping he would approve of it, and it kind of broke my heart to see that he disagreed with it. And I said, I felt that his analysis was good enough, and I couldn't, in good conscience, ethically dismiss it. And in fact, I have to approve it provisionally and say until someone else can find a flaw in it, I'm going to have to provisionally say it's we have to respect what he has said. Now, I hate in personal matters, I try not to ask people about the religious or metaphysical personal views and their views about creation, but because this is kind of the topic of the channel, I think it out of the courtesy of the readers, Jordan, if you could express maybe a little bit about your personal views, just to alert them. I hate putting people on the spot about their personal beliefs or whatever, but anything you think might be relevant for them to know, just to give them a heads up.
Sure. So I'm an atheist, by which I mean I believe that no gods exist. I used to be, or at least I used to identify as a Christian. In fact, I was a young earth creationist for most of my upbringing into my early adulthood. I guess I've been an atheist something like 8-10 years ish. But I feel like my background gives me a unique perspective among, well, perhaps not unique, but I think it gives me a good source of empathy and epistemic humility. So, yeah, I'm of the opinion I consider myself a skeptic. That's very important to my identity, and so I'm open to being convinced on just about any claim, no matter where it comes from. I just want good evidence. So.
Well, it's been a long time. Thank you very much. That's all we need to cover for that. It's really been a long time since we saw each other. The other gentleman's first name was John or something. Jonathan.
John. Yep.
He was a geochronologist. And again, I wanted to offer a sincere public apology to Jordan here that, I didn't handle the show well. I didn't give him adequate time. And I'm very, very grateful that, he overlooked my oversight and my mishandling. And, that he gave me a chance then to come back on this channel and showcase a very substantial investment of time that he made on this project, for which I'm extremely grateful.
Water under the bridge.
Well, thank you. As I said, there are times, it's a creation researcher. There are times you think you're right, and then someone comes along and just says, a big pause. Dr. Dan has come on my channel. Yeah, thank you. It's water under the bridge. I appreciate that. Dr. Dan had come on my channel and he said, no, Sal, there's some things about, what you're saying I don't think are quite right. And just like, bummer. I think Dan, sometimes, I said, some of the things I thought I can't think of as forcefully in light of what you said. And so, this is another one. I think it's valuable to temper expectations. I have a professional responsibility, because people do look at me and the things I say as reasonably authoritative, and that's scary. And if I misspeak, I have to try to correct it as quickly as I can. I try to stay close to textbook stuff as I can, but given the nature of the creation evolution controversy. I have to be kind of out on a limb there for a lot of things, but I try not to be too far out. So honestly, there's been so much that's happened since we've talked. I've sort of forgotten the details of the Rotta paper. Perhaps you could describe it, even though I'm the one who brought it on the table. You're more intimately acquainted with it than I am. And anytime you need to put up stuff on the PowerPoint, I can help you with that.
So I've got a PowerPoint to share, and part of that is me going over Rotta and his paper and his claims and stuff. I can just start the PowerPoint if that's all right.
Sure, go ahead.
All right. All right, so I figured I'd start by talking about the problem that we're trying to solve, or that Rotta was trying to solve, and to substantiate from a young Earth creationist perspective why I think that he's incorrect in his methodology, and then I'll follow it up with my own methodology. So the problem is that there's carbon-14 in coal, and coal, according to the broad scientific community, is made of ancient biomaterial. And carbon-14 occurs naturally in the atmosphere. As you may know, it is radioactive. It has a half-life of 30 years, thereabouts. So if the coal formed with this carbon in it, if the source of carbon-14 is from the material, the dead plant and animal material that it formed from, then all of that carbon-14 should have decayed away long ago if this is millions of years old. Yet there's some there. So what's up? So some alternative explanations. So the young Earth creationist explanation is it was there when it was formed, and it's still there because it's young. Some other alternative explanations would be contamination, experimental error, and if the C-14 was generated within the coal. So first, what is C-14? How do we get there? The primary way carbon-14 shows up is when nitrogen-14 absorbs a neutron through this reaction. So it absorbs the neutron, becomes carbon-14 that after a proton is kicked out, the carbon-14 decays back into nitrogen, and it decays back to nitrogen. You've got the equation up there on the screen, and the cycle continues. So, in the atmosphere, that happens when neutrons are knocked loose by high energy photons, but any source of neutrons will do. So the radioactive alternative is that the uranium is generating the C-14. Uranium can emit neutrons when it spontaneously fissions. It doesn't spontaneously fission very often. Usually it emits helium, an alpha particle. But every once in a while, it does spontaneously fission. Coal tends to contain uranium in trace amounts. And so what this would look like if you had, imagine the background is coal and you've got a uranium atom, bunch of carbon atoms, because that's mostly what coal is, and then some nitrogen hanging out. And the uranium fissions, kicks out 2 neutrons. The neutrons bounce around. Because carbon doesn't absorb neutrons very often. Usually it'll hit it and then keep bouncing. So it'll keep bouncing until it hits some nitrogen. The nitrogen absorbs it, becomes carbon-14. That's how it goes.
Can we pause just a little bit?
Yes.
First off, I should have said something earlier, and in some respects it shouldn't matter, but to me it matters. I want the audience to know that Jordan is a nuclear engineer, or studied it, mechanical. So this is something he loves.
Yeah.
Okay. Beyond just the technical qualifications, I score something much in someone's favor if it is a topic that they just love and they just want to talk about it all the time.
Yeah, I usually mention that as a disclaimer. I forgot to this time, but I am a nuclear engineer. I'm just an engineer. I'm not a nuclear physicist. I don't have a PhD in anything. I have an undergrad degree. So there's many smarter people than me out there. So perhaps I've made some mistake, and one of those smarter people will be kind enough to enlighten me. But yeah, I do find anything related to radioactive decay super neat. So
Yeah, so this is great. Okay, so my background is in applied physics and biology, but I did not have any nuclear stuff, which is amazing because Johns Hopkins supposed to be a great physics school, Nobel Prizes there. They don't have particle accelerators, they don't have reactors, so they do a lot of stuff with uh, like cosmology and theoretical stuff, a little bit of condensed matter physics. But I just wanted, I mean, as Jordan was going through this, I said, wow, I'm impressed with his background in, um, I could tell this is very educational for me. So I just wanted to pause for that. Now, if I may just, going back to the diagram, and I will try sometimes to, kind of I'll try to minimize the interference on the screen, not have too many comments if it's going to cover something up or our pictures. Could you
Yep,
go back one screen?
absolutely. And feel free to pause me and ask questions because um, it's, as you know, it can sometimes be, you can take things for granted and not realize that not, you know, you can be speaking something that other people don't understand. My wife is usually my sounding board for stuff like that. But
Okay.
over the years, I think I've contaminated that pool.
Well, we'll work through it. So there is the xenon, I think, and SR. Are those just random? That has
Yeah.
really
So the way it goes is you're kind of like seeing it through time. So the uranium fissioned, it can fission into a lot of different things. Um, One of the pairs of things it can fission into is xenon and strontium.
okay.
There's like a stochastic distribution, so there's no telling exactly what it's going to fission into, but it'll fission into some set of isotopes with a probability. And xenon and strontium are two of the most common.
Well, let me just introduce Redeem Team. Thank you very much for joining us. We have Schnoyl, who is a graduate student in computer science, and then we have a chemical engineer and redeemed here team here. So this is great. We've got our nerd team here. If I may ask, so the dotted lines are the neutrons, and they bounce on carbon. That helps slow it down. Is that correct? So that it could be absorbed by nitrogen.
Yeah, so that process is called moderation or thermalizing. So whenever the neutron hits carbon, it slows down. It imparts some of its energy to the carbon. Um, in nuclear reactors, that's often achieved with water, but graphite is another way it's achieved. It's not technically necessary for it to be absorbed by the nitrogen. If a fast neutron were to encounter nitrogen, it could still be absorbed. But as a general rule of thumb, it's easier to do absorptions with thermal, meaning slow neutrons, than it is with fast neutrons. So,
And I'm going to try not to bog down the conversation too much, but this is very educational. Can the neutron actually just kind of go through a nucleus or just blow it apart without being absorbed? What will happen
uh,
if the nucleus of nitrogen and it's too fast and it doesn't get absorbed? What could happen?
so if it interacts, so there's a lot of different ways that a neutron could interact with a nucleus, but the two primary ways that it's going to happen would fall into some kind of scattering, meaning it bounces off, or an absorption of some type. That absorption could lead to different modes of decay depending on what is doing the absorption. But broad strokes, you can the vast and overwhelming majority of the time it's either going to hit it and bounce off or it's going to be absorbed.
Okay. All right. So go. Thank you, and we can move on now.
So that's the path. Your neutron's been bouncing around, it gets absorbed by something. That's how carbon 14 is born. Now, what Rotta was trying to do in his paper published in 2003 in the Creation Research Society Quarterly, he was trying to show that the source of neutrons, being the uranium, is insufficient. So, in order to achieve the concentration of carbon 14 we have, you would need a certain amount of neutrons. And what that amount depends on is how quickly the carbon 14 is being lost and how quickly it's being activated. So, if you think about it like a tub, if you imagine that the carbon-14 or the coal is like a tub and it's like filling up with water. There's a hole in the bottom. If the hole in the bottom and the amount coming in are the same amount, then the water level will stay the same, right? And that's what you would get if you reached equilibrium with uranium decay. If the uranium was producing carbon-14 at the same rate that the carbon-14 is decaying, then you'd reach equilibrium. And he was trying to show that the amount of neutrons produced by the uranium is insufficient to do that. And his number was he said that the concentrations of uranium were a factor of 100,000 too low to produce enough neutrons in order to generate C-14 in sufficient quantities. Go ahead.
Now, if I may, if we just go before we get any farther, just if you want to comment on it now or save it till the end, I just wanted to say I'm interested. I'm sincerely interested if there's any experimental technique that could verify one viewpoint over the other.
Well, I mean, you could yeah, I could imagine you could create you could embed a known neutron source in coal, or honestly fire a neutron beam at a coal medium or a similar medium and see what happens, and then determine, or even it wouldn't necessarily be like physical, but you could I don't have access to these, but you could use neutron transport codes like they use in nuclear reactors, which are extremely well verified. Like reactors the world over have been using them for decades. In fact, and they're so accurate at this point that if there's a discrepancy between what's being observed in the reactor and what the simulation tells you, then you can pretty much guarantee the problem is with your measurements, not with the simulation.
So the neutron code is a computer algorithm. It implements a computer algorithm.
Yeah, so it's a Monte Carlo simulation, and what that means is it basically generates a ton of neutrons in the code and has them virtually fly through some medium, and basically tracks every interaction it would have, the odds of it being scattering versus absorption versus whatever, and basically tracks the neutrons through their entire lifetime through the core or the medium. And you could certainly modify that code to simulate something like this. That's well beyond the scope of what I could do with my free time and the software I have available to me, but you can certainly do it.
Okay, no, this is really important. You know, I'm a big advocate. It's like, is there a way, you know, we could have two sides of an issue. This is the way to calmly and rationally resolve disputes. If there are things where we could run an experiment, or like as you said, like with something that is considered very high quality, like this neutron, you call it the neutron code. I think that's the way to go.
Yeah, it's a Monte Carlo simulation. The MCN something. It's Monte Carlo neutron, and I can't remember the rest of the acronym.
Okay, no, this is great. Thank you for that response, and please continue. Thank you.
So the Rotta paper, I read it, and at first blush, it seems pretty convincing because he uses equations that have like the units match. So like when I was going through the paper, just kind of like when I'm checking the math, the first thing I do is, well, are the equations like talking about the right things, right? Do the units match? Those sort of like quick checks, and they were all right. And like I wasn't sure what his equations were, but they were like they made sense in context. So I had to dig in deeper. It took me a while to figure out because he doesn't come out and say what kind of equation he's using. But I was able eventually to parse together what he did, and he used what are called thin plate assumptions. So I've got a picture on the PowerPoint. Which
I don't know why it dropped. I'm sorry.
No problem.
It might have. Just try to bring it up again, and I'll post it.
I can unshare, or here, let me reshare it. So this is the equation. He starts there at the top, and I rearranged it to the thing you get on the bottom, which is a more typical equation that you would see in the wild. They're equivalent equations, but the bottom one is more like normal of what you'd see. And what that's describing is this situation: a neutron beam shooting at a thin plate of some material and then attenuating. Um, this
And just for
equation,
the reader's benefit, I mean, viewer, attenuating meaning reducing the velocity of the neutrons,
the number
or
of neutrons. So
okay,
like,
the number. Thank you. I'm glad we clarified that.
so you've got your beam going through it. It's got so many neutrons. It hits this plate. Some of them are going to interact. Most of them are going to pass through, probably, depending on how thick your plate is. And so some of those neutrons are going to be absorbed or scattered away, not part of the beam anymore. And what's left over is the attenuated beam. So a thin plate assumption is good if because it's much simpler. You don't have to deal with a lot of effects like there's effects when you get close to the edge of a plate or medium. There's funky things that happen there. But if the plate is sufficiently thin, those don't matter. You can have more than one interaction in a thicker medium. Whereas if you have a thin plate, that's unlikely, so you can neglect it. And that's another reason why it's really nice. So it's really good to use in a lot of situations. Unfortunately, for coal, it is not a good assumption. Um, so the reason, hold on. So the reason it's not a good assumption, and I might say this way, my slides might be out of order, but anyway, the reason it's not a good assumption is because coal is not a thin plate. Seams of coal are like some feet, sometimes meters thick. And the distance that a neutron is going to travel in this medium is about a centimeter before it has an interaction. So it's definitely not going to make it the whole way through without some kind of interaction. Um, and so what Rotta's paper does in essence, because it treats coal as if it were a thin plate, it implicitly includes a lot of neutron leakage. It assumes that most neutrons are going to escape the medium because it's treating it as if it were a thin plate where most of neutrons are going to escape that plate. In fact, and it's kind of funny because in the paper, Rotta himself, when talking about neutrons from like exterior sources, says that the neutrons from the outside wouldn't penetrate more than 25 to 50 centimeters, which is far less than the thickness of a seam. So like in his model, and this isn't on purpose, I'm sure, but his model is implicitly treating carbon as if it were more porous from one direction, which it just isn't. The skin is just as thick from the inside, like Guardians of the Galaxy. So um, you can't treat it like a thin plate is the basic error, and that's why he gets a result that's so incorrect, because he implicitly includes a ton of leakage that isn't realistic.
Oh, okay. I'm sorry. I'm just a little slow here. So, what is
No
a
problem.
coal seam?
So a coal seam is like the name for the coal down under the earth. Like it's like a band of coal running around underground.
All right, and you're saying that what is bigger, is the coal seam bigger than 25 to 50
Oh yes.
centimeters or
So
smaller?
they vary, but coal seams can be several feet, sometimes several meters thick.
Okay.
Um,
So
so
Rotta himself says that neutrons from outside would not penetrate more than 25 to 50 centimeters before an interaction. Is that correct?
yeah, so what he was talking about there was the idea that neutrons from other sources outside the coal could be bombarding the coal and generating the nitrogen. And he, I think correctly, says that that wouldn't be a serious source because that would only generate carbon-14 on the edges because the neutrons wouldn't be able to penetrate, right?
Okay,
Well,
okay.
for the exact same reason, they're not going to escape either. So what's going to happen is those neutrons are going to bounce around, and they're going to keep bouncing until one of three things happens. When a neutron is emitted, it's either going to escape, which is not likely because of how thick these seams are and how likely an interaction is. It's going to be absorbed by something, or if it somehow managed to last about 15 minutes, it would decay into a proton. But that's extremely unlikely.
Okay, so
So
actually everything you've said kind of to my own my own regret, I have to agree with you there. So I'm not, I'm not going to slow down the discussion just to dispute, because you got my agreement there. This would seem like this right in itself would be good for that neutron code Monte Carlo simulation. Just this part alone, that second sentence there.
Right.
We
So
there's 25 to 50, and that would, you've already, I think, certainly cast severe doubt on the thin plate assumption, given what you just identified. So, guys, any creationists out there, if you want to contest this, you have to contest the logic. And I can't find a hole in what you just said, Jordan.
yeah, there's no question that the thin plate assumption wouldn't work. I mean, thin plate means just what it says, a thin plate of a 15-foot thick plate is not a thin plate by any definition. And yeah, so the assumption that most neutrons in your beam are going to make it through without interaction, which is what kind of the thin plate assumption relies on, just isn't going to work. So it's not appropriate. The situation violates the assumptions of the model.
Well, I mean, just, and I already mostly agreed with you, but I mean, just from the geometry of it, I can see that, kind of like, say, if you had a center of the seam, it could that neutron would have more probability of being absorbed, whereas if there's uranium kind of toward the edge of the seam,
right. If there was
and
like a uranium atom kind of hanging out on the edge, and so when a neutron is emitted, they're going to be emitted roughly in equidistant in a sphere around the emitter. So the ones that it's near the edge and they get shot out like towards the edge, well, I mean, that's probably about a thin plate, but that's a very small subset of the total number of uranium. We're more concerned about like the 99% of the coal elsewhere, not the
yeah,
1% on the edge.
this is where it gets a little nasty. Is you have to integrate all the probabilities and positions, and we don't have to do that. But I'm just saying, at this point, I think you've made a very good case, and if you, by the way, how long is your presentation going to be? Because I want to make sure I respect your time here.
So I've got some math for what I think a better model is that I can run through that concords with observations.
Would it be another half hour or so, or 45 minutes?
How long do you want me to take? I can adjust it to however long you want to give me.
I want to give you as much time, because I have these little rabbit hole questions that I'm really curious about, because this is a great opportunity for me to learn. And I have one burning question. Can neutrons, I would presume neutrons can be affected by gravity. I mean, they'll fall to the bottom toward the Earth.
So neutrons have mass, and like any particle with mass, they are subject to the forces of gravity. However, because they have very little mass, they aren't much affected by gravity. And so other forces are going to far and away overwhelm any effect gravity would have. They're not subject to electromagnetic forces because they're not charged. But when they're thrown out of a uranium, let me put it this way: a slow neutron is moving at 2,500 meters per second. So gravity just isn't exerting enough force on it to significantly slow it down.
Meaning, if it bounces upward, it's not gonna.
There's no appreciable difference between moving against gravity or against the gravitational field or with it, so far as the neutron's concerned. It's such a small particle that the force of gravity is negligible.
I mean, it would have the acceleration of gravity on it, but because it has no velocity. Yeah. Anyway, it's neither here nor there. And just to explain, the reason I brought that up had nothing to do with our present conversation. It had to do with a particular theory of cold fusion and talking about neutrons dropping out according to gravitational force. So thank you for
okay. So, let me put it this way. The neutron would probably decay into a proton before gravity mattered, because the neutron doesn't last forever. A free neutron decays into a proton pretty quickly, about 15 minutes.
Yeah,
So
that's the figure I kept hearing. Okay,
yeah,
that had nothing to do with it, and I'll try not to derail it, but every now and then, because this is such a cool discussion, I have to just ask.
yeah.
All right, but please, I think you can sense I'd like this to be a detailed discussion, and just um, everyone watching will feel comforted that we were thorough. We weren't skipping over things or trying to pull the wool over people's eyes. So um, I don't want you to feel rushed. The only reason I asked if you had time is I knew I was probably going to ask a lot of questions, and I just didn't want you to get bogged down and you end up being here 4 hours. So I wanted to respect your time. That's why I did ask.
Appreciate that. Well, let me jump on to my model then. So let me put over the math. Hold on. Get my calculations up over here. So before I go into my calculations, let me explain my model. So I'm going to assume that every neutron that's shot out is absorbed. No neutron escapes. And the reason for that is what I've been describing. The neutrons interact frequently in the medium. They go through past a lot of atoms, but there's just so many atoms. They get only about a centimeter on average before they have some kind of interaction. And that interaction is going to cause them to bounce around like pinballs until one of those three conditions happens. And most neutrons are going to be absorbed because
Okay, so
you've got.
if I may weigh in here, so this model is valid when you have a cold seam that's say, um, maybe 10 times larger than 50 centimeters. 50 centimeters isn't that much. So if you have a big coal seam, this model's definitely adequate. Is that a fair characterization?
Yeah, I don't know how thick the coal seam would need to be for it to stop being adequate. Um, but my guess is that so if it coal seams, like I said, can be several feet to several meters thick. Um, if it were 50 centimeters, that is what? Because for Americans in the audience, that's 20 inches. So that's like a little bit less than 2 feet.
Okay. Okay. But there is definitely a situation where if the seam is big enough, this would be a valid, very valid approximation. And so I'm
Sure.
fine with it. Okay.
Yeah. So for a thin seam, this probably would not be a good approximation. But for a sufficiently thick seam, and I don't think you'd need to be that thick to be sufficiently thick, um, this allows us to not do a neutron transport calculation, because if the medium is very thin, then you don't need to do it because most are going to escape. The medium is very thick, you don't need to do it because most of them are not going to escape. It's only when you're in that icky middle region that you have to do all kinds of Monte Carlo simulations, which
Okay.
is what we're trying to avoid.
Okay. This is perfectly fine.
So, zoom in real quick. That's just going over my assumptions, which I've already just outlined to you. Okay, so I'm gonna breeze through this math pretty quickly, but here's how it works. So, in order to know how many neutrons are absorbed by your nitrogen, you need to know how many atoms are in your medium. So, in case anyone's not aware, this is how you calculate that. You've got the mass of the thing times Avogadro's number over its molar mass, and that gives you a number of atoms in whatever volume you're looking at, right? Um, the activity of a radioactive isotope is given to you by this equation. The activity equals the decay constant, which most people are probably more familiar with the half-life. Half-life equals natural log 2 over decay constant. So that's the relation between the two things. So the activity of any atom, any radioisotope, is equal to lambda times the number of isotopes you're looking at. In this case, the number of uranium atoms based on the concentration in uranium is 6.75 times 10 to the third becquerels, and that's just a becquerel is just a very fancy way of saying decays per second.
Thank you.
I mean, you have to use jargon to make yourself sound smarter than you are, but that's all it is. That's what a becquerel is. That's how many fissions are happening for the uranium-238, or sorry, that's how many decays are happening. You'd multiply that by the fraction of decays that are fission, as opposed to the much more prevalent alpha decay. And then multiply that by the average number of neutrons you get from a fission, which is 2.5. And this tells you how many neutrons per second you're getting, a little bit less than 1. So at equilibrium, the number of carbon atoms produced is going to equal to the number destroyed. So the way this works is your uranium spitting out neutrons, and it's building up carbon-14. The more carbon-14 you have, the faster it decays. Its decay half-life doesn't change, but when you have more of it, you're just going to have more decays per second because it's exponential. And eventually, so you'll build up, and as it's building up more carbon-14, the decay gets faster until the point where the decay is happening at the same rate of production, and then you reach equilibrium. So that means that if we're producing 0.92 neutrons per second, and every neutron is absorbed, then the activity would be 0.92 becquerels for your carbon-14. And this isn't talking about poisons. I'm going to get to poisons in a second. So that's the activity of carbon-14 in coal. If all of the uranium was the neutrons from uranium fission were absorbed, and you can do some math to turn that into what would be like an apparent age if you were to radiocarbon date it, and that would give you an age of 42,500 years.
Can we pause here?
Sure.
And let me just tell the creationists out there, I'm interested in this, but it would be irresponsible for me just to throw stuff because I can only raise concerns. I'm not trying to just say this is totally wrong. But I don't know that we can. Okay, I'm just thinking out loud here, and I hope you forgive me, Jordan, because I try to think through this like an engineer. Is it possible that the neutron will eventually escape? It'll bounce around, slow down. It doesn't necessarily mean it's going to be trapped in the seam. Is that correct?
So it'll bounce around until it escapes, is absorbed, or decays. Decay's not going to happen before either of the other two. It's not going to take 15 minutes for it to get away.
Yeah.
So it's going to bounce around until it is either absorbed or escapes. Because it's having interaction every centimeter, and because I'm assuming the seam is thick, like very thick, such that it may as well be infinite, then that's why I'm assuming that every neutron is absorbed. In reality, some fraction of the neutrons are going to escape.
Okay.
I think it's going to be a small fraction, but some fraction is going to escape, sure.
I think it could be a larger fraction. I think there's a possibility. Okay, so I'm not going to contest it, but go on.
So imagine this. So it goes a centimeter, it has a scattering. That scattering is going to go in some direction. It could be basically any direction. So the absolute, if it took a centimeter and if it shot towards the end, right, towards the edge, and if it got so lucky that every single scattering was 180-degree scatter, which it won't be, but if it were, then at minimum, it's going to have what? 100 interactions on the way out? And that's absolute best case scenario on average. Reality, it's going to hit and it's going to probably be deflected, not directly towards the edge, but back a little bit. And it's going to bounce around at random. Now, just like a Plinko ball or a puck, sometimes it's going to bounce around to the point where it works its way all the way out. But it's not like it's bouncing around a couple times and leaving. Like we're talking, it's going to have a ton of interactions on its way out. And at no point, if it ever hits a nitrogen-14, a boron, or a sulfur, then then at that point it's probably going to escape or get absorbed rather.
Okay. I just if I could say it from my perspective, you have kind of a similar situation with it, it, it's not exact. If it were just bouncing around and not being absorbed, it would be like a gas escaping. Um, when the container is just like uh, gone. But because there's absorption, that's the part we don't know. So
Well,
I I honestly, I mean, just for my comfort, if it could be modeled how much escapes, I would. I'm just saying it would make, you know, I think that would help settle the issue. And I just have to put that out there. I'm not saying you're wrong, and I'm not saying that my concern um, uh, is correct. I'm just saying that would make me feel a little more comfortable. I will grant, for the sake of it- you know, for the sake of argument, that you're correct, because I do think the way you've modeled it raises more concern for Rotta's paper than the concern I raised. So I'm going to go with you where you are. I just have to, just for completeness, mention that, and then we can
I'm
go.
I'm assuming that I would probably feel comfortable using this kind of model on a seam that was about a meter thick or more, um, without having done any neutron transport equations or run MCNP. That's the code I was trying to think of, MCNP. Without running any MNCP, because I have I may or may not have a copy of it floating around somewhere, but I don't have it installed on my computer.
Okay.
But
Oh, go
uh,
on.
so with the mean free path being 1% or less of the total width of the medium, I don't know. Seems pretty reasonable to me.
Yeah,
But
and for let's just look at this as like professionals and saying, what would we have to do to really verify what's going on, to take it to the next level, and that's about all we could do. And see, Schnoil said there should be an experiment on this, and like the simulation's the next best thing, as you said, MCNP, and it might even be better than any experiment we could run given the accuracy of what you described.
it would
Um,
certainly cost less.
yeah, yeah. Um, I'll tell you also why I'm interested in this, and this is looking a little bit forward. Um, this could at least tell us what situations, if we do find C-14, um, could we possibly determine, like, how many parts per million uranium would we have to clear out to make sure it is a residual C-14 and not the result? I mean, how many neutron sources is the more accurate term? Not just uranium. How many neutron sources do you have to eliminate? How far away? And this is like kind of the first step toward, you know, uh, figuring some of this out. So this is why I would say, okay, um, and this is what I've been doing at some my creationist discussions. If you say you have C-14 in here, I think they need to take your model, Jordan, and say, uh, if you have anything in the vicinity with this much uranium, you have to be concerned that there is a radiogenic source. Is that the right term? That's
Yeah.
creating the C-14. And so
Go ahead.
I actually look at your model as actually possibly helping some of the creationist detections. It may eliminate a lot of them, and it's like, okay, you got to take it for, you have to respect what you've come up with.
I've got one more piece, and it won't take long. Just adding in the neutron poison, so like another 5 minutes, and then I can answer any questions anybody has. So that part I just went over is assuming that the only thing around are carbon or stuff that's going to scatter and nitrogen. But in fact, in coal, as when I originally did my first part of the equations, Sal rightly pointed out that there's boron and sulfur, which are poisons in the coal. My original guess was, well, they're in trace amounts. I don't know, maybe it won't matter. And but I went back and I added them in. So here's what this looks like.
Thank you very much. If you could explain for the viewers, actually, the poison was a term I was not familiar with when you used it. What I did was I went into the National Institute's National Standards NIST and looked at the tables. And I actually was surprised how much just a trace amount of boron could. I
Yeah.
mean, you know,
Well,
so
there's a reason.
the word poison means, and I'll let you explain what poison means.
So a neutron poison is anything that will absorb a neutron without producing fission. Um, and it's kind of from the nuclear industry. Poison is bad. You don't want poisons in your reactor unless you put them there, because we use boron. I'm not part of the power industry anymore, but part of the nuclear generation industry uses boron in like the water of a light water reactor, or you might use it as like in a rod to control your population of neutrons. So it is a
Go
sorry,
on.
it's a highly it is a highly absorptive isotope. So
If I may ask this, and this is just for completeness, if it's a neutron poison, that means it absorbs it. You'll have a new element, or you'll have a new isotope at least. Is that correct?
correct. So
Okay.
a neutron poison would be any isotope that is likely to absorb a neutron when it has an interaction.
Okay, you know what I remember now? Because after you sent me this, I looked it up. And I was wondering why they were trying to, like when they had, let me just pause here. This is a historical thing, and this is a nerd thing. When they first made the first nuclear reactors, they had a hard time making graphite. And I'm like, why? It's just carbon. And they needed a special chemist to be able to remove the boron in there.
Because you don't want a poison in your moderator.
That's right. That's like, what was going on with that? I mean, and it's like, those are just like such tiny amounts. And that's when I began to say, oh my, it was significant enough that they couldn't get the first nuclear reactor to work until they really like purified it. I mean, how many parts per bazillion are we talking about of boron per?
So I had to dig for a while to find a number. I eventually used a number I found in the study on boron distribution and chemical form in coal, 2006, from the Mining and Materials Processing Institute of Japan. And they said that natural boron has a concentration of about 44 parts per million in coal.
That's like nothing. It's like, if my water were that pure, I'd be pretty impressed. I mean,
but the reason it has such an impact is because its cross section is big. And so cross section is a property of an isotope, and it basically means how likely a reaction is to happen of that type when an interaction occurs. So you can think of it like a target. How big it's actually its units is of area, centimeter squared, or barns. And barns is 10 to the a barn is 10 to the negative 24 centimeters squared. And so that you can think of it like a target, like how wide is the atom or the nucleus from the perspective of the neutron. It's not actually physically like that, but that's good enough to get your visualization. So,
please go on. And I'm sorry, I can't always tell when someone's completed their sentence.
No problem.
I'm not trying to interrupt you. If you had something more to say, I have something else to say about that.
Go ahead.
Will there be a point that all the boron, if it's a poison, and we have all these neutrons floating around, can it eliminate the boron at some point?
Well, I mean, the boron's going to be destroyed every time it absorbs a neutron. But
okay, so it's going to be destroyed. How? Okay, go on.
But because the uranium is producing so little over time, there's just not much uranium, and it doesn't decay very fast. So I don't know. I didn't run calculations to see how long it would take, but a long time, I would imagine, for it to destroy all of the boron in the coal.
No, well, you can tell where I was headed with this. Probably that I would be interested to see the proportions of boron. That might be indicative of how much we could compare the amount of uranium and the concentration of boron. It might be a clock of some sort.
Well, I think the problem with that would be that the concentration of natural boron varies significantly, in coal, irrespective of anything else. So it'd be difficult to say, like, I don't know that there's any way to tell how much boron was there originally. Um, Unlike with other radiometric dating methods where you can get past that, I don't know that you could get past that in this case, particularly since coal is not like a sealed system like a zircon crystal, even in hypothetically,
And I don't know what the daughter product of that reaction would be, or the products of a neutron plus a boron. But we can move on.
I don't know, but I could find out if I just pulled up the chart of the nuclides. I don't know what isotope natural boron is usually in. Let's see, boron atomic mass of 10, so it's probably boron 10, right? So if let me put it over here so everybody else can see what I'm doing.
If you could pause for just a minute, I have a little wound I need to treat, and I'll be right back. I have to go get some Benadryl. I'll be right back, Jordan.
Sure, I'll entertain with my dulcet tones. So, anyways, back to the coal issue. The way the neutron poisons would basically serve to suck away neutrons from your population. They would unproductively be absorbed. And so the effect would be that you'd have fewer neutrons that could then go on to produce carbon-14. That would be the mechanical effect.
Okay.
And so and what it would do is it would basically attenuate your hypothetical beam of neutrons, right? And so since we're treating our coal as if it were infinite because it's sufficiently large for all neutrons to be absorbed, then all that really matters is how quickly the nitrogen is going to absorb things versus the boron or sulfur, which are the two primary neutron poisons naturally present in coal. So the way you'd calculate that is by determining the beam intensity. So your beam of neutrons are going through the uranium. The formula for beam intensity is this guy right here. Your intensity equals e to the negative sigma x. Sigma, that is a sigma, right? The 3 looking thing. Pretty sure it's sigma. I don't know. Doesn't matter. That thing. It's what it stands for is macroscopic cross section. And what that is the microscopic cross section, which is how likely it is to do the thing. We talked about the units of that as barns, multiplied by the number of atoms. That gets you your macroscopic cross section. So e to the negative macroscopic cross section times the thickness of the thing. In this case, thickness doesn't actually matter as long as all your thicknesses are the same, because again, we're just looking for relative absorptions. So I just took it to be a centimeter. Doesn't matter. The units cancel out anyway. So if you look at your attenuation due to nitrogen 14 over the attenuation due to nitrogen 14 plus sulfur plus boron, it comes out to be about a third, 32.32%. So that means that 2/3 of neutrons are absorbed by boron or sulfur. So they
surprised me that it would be that large. Is that correct? That
yeah,
seems like a significant number.
I was surprised too, honestly. I wasn't expecting, even though boron does have that ginormous cross section, I wasn't expecting such a large effect. But there it is. Math doesn't lie. So
well, the thing was, that's what, when I was just looking at all this as I was reviewing your paper and your work, and I looked it up, and I just looked back at the first original reactor, and they said that was a big deal trying to remove the boron, and I'm just like, well, there's hardly anything there, and and it was like that trace amount seemed to be enough, and I went through the calculations. I said that is huge, and I said, I think I'd rather Jordan do this, because I think this is your field, and I was like, could it be that much? And so, thank you for doing this. And I wanted to just salute your integrity for doing this, because I was the one who requested it, and you went and added it. And, I just wanted to salute that. I felt you're trying to be as fair to this as possible. And I just want to let the readers know that, the viewers. So thank you.
if you basically plug that back into the calculation above, which I already talked about, and all you do is like reduce the neutron population by that much, then your equilibrium concentration of carbon-14, if you were to date that, will get you an age of 51,000 years.
What was the original one before you had?
It was 42,500 years.
Right. Yeah.
Now,
That's
something
right. Okay. Yeah.
something to keep in mind here for those who aren't familiar with radioactive decay is it's exponential. And so, but the error that is produced by something like this is flat. Okay. So like it's a constant amount of C-14 concentration being produced by the neutron, by the uranium. Whatever that concentration is, whether it's very small or very large or whatever, there is some equilibrium concentration of carbon-14 due to neutron production. And so that's going to introduce a static amount of error. But that static amount of error does not translate one-to-one to years. So if your sample is extremely old, your small amount of error might be a 10,000 year error. If your sample is very young, that small amount of error might be a year or less, because you've just got the error compared to the total amount of C-14 would be much, much smaller in that case. So the older your sample is, the more those sources of error can swamp out the signal. That's why it's carbon-14 dating isn't used really past like 60,000 years, I think, is as far as anyone is willing to go. But usually it's like 40,000 years, you're starting to get into dangerous territory. You have to be really careful and have a really good sample. So to that end, just as an aside, I was curious. Okay, I know that if you have if you had a sample that comes out as about 50,000 years, that could all just be the error. The error is sufficient to possibly account for all of that activity, such that like if you dated something that had no C-14, you might get a date of 50 or 60,000 years just because it's such trace amounts. And so if you added that amount of error to this number, that could get you down to, this is my super messy spreadsheet that I did all these calculations on that means nothing to anyone but me, which is why I wrote that document. You could get down to 45,000 years with that amount of error. So moral of the story is, if you have a thick, by thick I mean several feet or more, seam of coal, such that your neutrons wouldn't escape, then you got a date somewhere in the mid 40s, then I think you could easily explain that with uranium. The Now, I will say that the concentration of uranium varies significantly in coal seams. It's not like a constant thing. So I took like average values for that. I took average values for the boron concentration. All of these things vary significantly. And so I would expect that like if you had a coal that has a higher than normal concentration of nitrogen, for example, and a higher than average concentration of uranium, you could get a date that's much lower because that equilibrium is going to be higher. Conversely, if it was not well enriched with uranium or had a low nitrogen concentration or a higher boron concentration, then the age would be much lower because for the same reason. So this
was excellent. Is that mostly your presentation then? Because I noticed you stopped. Okay,
I'm complete.
If you could, first off, I'd like to ask your permission and blessing if I could circulate this among my colleagues.
Yeah, I'll email you links to everything. I'll email you links to this document, to the thing, and I can email you the spreadsheet too. I can't guarantee anybody but me will decipher it, but I'll give it to you.
Yeah, I'm going to, unfortunately, I don't mean to be too harsh, but the number of creationists that work on this that are qualified is so tiny, and they, I'm probably the one that has invested more in this discussion than anyone on the planet on the creationist side, and that's just the way it goes. And it's not had the most clean history, and I can't promise anything. I might be the only endorsement you get so far, but I do feel that there's value. They might be able to say we could use this to help say, like, if we do find some samples that are isolated away from uranium sources, we might need another model to say, okay, what are the other sources? But this is a start. And just for the viewers' benefit, the reason that I'm not just because of faith, you know, you have to have at least enough evidence to make you think that there's a chance you're right. For me, it's the chemical dating. And I brought that up in the last discussion we had when John was joining us. And he said, yeah, that is something we need to deal with. One side has to, you know, the problem with a chemical date has to be resolved one way. And then, you know, like the stuff we're working on. And with the chemical dates, like with the dinosaur bones, if they find C-14, it could be the instrument error we're measuring. Could it be another source of radiogenic or whatever, or contamination? So, you know, I think I would like to be able to say, okay, could we take models like yours and say, okay, we've at least eliminated this as a possibility in the, you know, for when we made a measurement or discovery here. It doesn't mean there couldn't be other problems, but I think the responsible thing to do, like in the case of coal, is to say, hey, you know, time out. I don't think we can use this as a proof of young Earth. So I would not, I'd be reluctant at this point to say, you know, if I were teaching students, I would have to say, you know, you know, our side claims this is evidence of young Earth. I would have to point out to your paper and say, this is to your work and our discussion here that you've raised very legitimate concerns, enough so that I would not, you know, endorse that as a evidence of young Earth.
Yeah. So I wouldn't look at this. You can't on either side poke holes in a model and then say therefore my model is correct, right? So
Right.
I can't say because, for instance, the heat problem of, you know, of catastrophic plate tectonics eliminates that model. Therefore, my model is correct. That's not how it works. But that said, I think you have to. There's a tendency I see, and particularly in people who aren't, you know, classically trained, or, you know, they're kind of laymen, kind of like I am. There's a tendency to focus on the thing you're dealing with right now and never plug it back into the total model, right? So like they'll come up with an explanation for the thing that they're looking at, and then they'll come up for an explanation for the other thing that they're looking at. And so if a piece gets knocked out, it's not a big deal because they've got all of these other plates spinning, right? But I think there's a tendency to never look to see how many plates are still spinning, you know? And so I think that if you've got enough holes poked in your model, then it would behoove someone to take a step back and just ask the question. What the question I asked myself when I started doubting my young Earth creationist beliefs was, what's the simplest explanation for all of the evidence? Leave aside my philosophical commitments, leaving aside any beliefs I have up to this moment. What model best explains the evidence with the least amount of ad hoc assumptions? Because I decided in that moment to accept whatever the evidence told me. That's what I'm going to believe. And I think that's what you have to do if you're going to try to eliminate the bias within yourself. That's the only way to go about it.
And for myself, if I could explain to the viewers, I was an old Earth creationist, so I was right on Jordan's side as far as the age of the Earth and the fossil record, totally. But then people like Michael Behe came along, people like James Tour. I mean, not the modern James Tour, his predecessors. The James Tour is articulating now, and I'm like, I could still be an old Earth creationist, and I began to distrust a lot of the mainstream views, specifically for abiogenesis and evolutionary theory, still accepting the old, that the universe and the Earth were old. But because I'd seen such a big, you know, two big pillars of my worldview kind of eliminated, It made me explore. But I have told young Earth creationists, I said, this is hard. I don't think you realize if you're a professional researcher as I am, I don't think you realize how how problematic our models are. You can poke holes in the other side, but you still haven't proven yours. And you know, I tell you, I'm comfortable debating abiogenesis. I'm comfortable debating the evolution of eukaryotic stuff, eukaryotic components, and I feel that I will make a very good debate on that. You know, as far as the age of the Earth, it's tough. I have not been able to say that I could win it on purely evidential grounds. I can poke some holes on the other side, but it's still, there's a saying, you can't build your own house by burning down the other guy's house.
It's true.
And you know, I'm hardly even lighting much of a torch to the other guy's house at this point. So a lot of this is driven by faith, but just with enough evidence to keep me going. And I try to keep telling young Earth creationists, you're in for a battle. You want to prosecute this, you're going to have to fight a lot harder than you have for the abiogenesis debate. This is not easy stuff. And this is illustrated by what we walked through today. You looked at those equations and what you had to learn about nuclear physics. And I would struggle with it. And even a nuclear engineer, Jordan, told me that he spent 8 hours at least going through Rotta's paper. And I'm like, I'm not even a nuclear engineer, even though I have a background in physics. This would take me several days, if not a week, to get through it. The only thing I could pat myself on the back for was I said, let me look at those scattering cross sections, those absorption cross sections, and I felt I was able to actually add one little thing to Jordan's model. I'm like, yeah, that was pretty good, Sal, but you know, you still know this stuff well.
I when I was going through it originally, I was like, there are poisons, but I don't really want to deal with those. It's probably fine, you know. Like, I just didn't want to do it, but I did it eventually. I normally for like the heat problem and stuff, those calculations I did, I think, are fairly simple. This one, like the calculations themselves are simple. I think you probably the leaps you need to take wouldn't be intuitive unless you had a background in it. Deciphering, honestly, the most difficult part was figuring out what the heck Rotta was doing, because like I knew his formula wasn't like crazy, it wasn't bonkers, but like I just couldn't figure out what the hell he was trying to say. That took a long time.
So what was the name of that simulation again? The up
MNCP, I believe, is the name. Money or MCNP. MCNP.
MCNP. Okay.
Yeah, Monte Carlo N particle transport code.
Okay. Hard as it may be to believe, there are a few nuclear engineers in the young Earth community that might have access to it. So we'll just, you know, I'm going to go with what you said here provisionally. I think it's the ethical and responsible thing to do. It bothered my conscience if I'm, you know, not giving them what I think is, you know, not just the best, but at least, you know, kind of more conservative in terms of their claims. Because I don't want them to get burned, and they could get burned because if you did this calculation, someone else can come along and do the same and confront my colleagues. And then, you know, I'd rather they hear it from me and say, hey, you know, you got to temper your expectations about what the data is saying. So
I'm a nobody. I'm just an engineer. So if I can do it, definitely other people can do it. And MCMP would definitely be the more robust way to do this, because that would actually give you a quantity for leakage. And then you could do things like you could answer the question, well, how thick is thick enough where leakage stops being a problem? You know, you could definitively answer those kind of questions.
Well, this has been a great discussion. Let me see. I think I tried to advertise it on my main channel that you were going to be here tonight. And at first I was going to see if we could record something for the main channel, but you know, it's like, what would I clip out here to share it? So I just might mention it again in passing on the main channel that you did really good work on this. And also when when I talk about radiometric dating, I'm gonna refer to the work that you had done on this. So when you send me the links, I'll put it in the video description. I'll try to put it up on my website that's coming up. And thank you again for everything. I'll give you the last word.
Well, thanks for having me on, and thanks for giving me this opportunity to whip out my nuclear engineering math. It's even though it is work, I also enjoy it. And especially now that I'm not doing nuclear engineering, I'm business analyst for a bank now because they pay way more money. It's it's always fun to be able to like brush up on that thing I went to college for. So
Well, and thank you again. And I'll meet you briefly backstage just to say goodbye. So
sure.
thank you everybody who joined us in this nerd torture session, and take care, and God bless you. Have a good evening.